So that was our first approach, to try and find out when the first light in the universe happened by looking at its effects on the gas. The idea being that these first stars would ionize the gas around them. And unfortunately, we came up with somewhat contradictory answers. The quasars seem to indicate that sometime about redshift 6, lots of ultraviolet was coming from somewhere. On the other hand, the microwave background scattering indicated maybe it happened before redshift of 10. So given we've got a strange answer from that, time to use a different approach. Now it's time to use brute force. If we have a really good telescope and stare very hard for a long time, can we actually perhaps see these first stars?
Well, we do have a really good telescope. It's called the Hubble Space Telescope, several $billion telescope, and it can look further than any other telescope that mankind has ever produced because it's out in space. And so here is an image that it took called the Hubble Ultra Deep Field, where it spent a couple months looking at a patch of sky to go as faint as humanity can go at this point. And so you can see that there are literally 5,000 galaxies in this image. And because we have this interesting feature that the really distant objects will have all of their light absorbed by hydrogen, we can identify really distant objects simply by their color.
Just as we did for quasars. So we're looking for, in this case, galaxies which have the same sort of spectrum where all the light optical wavelengths has gone and maybe just infrared light.
So in this image, where we're actually looking at quite a big piece of the universe because we're looking so far away, we've identified 28, and I say the royal we here, 28 objects who appear to be at roughly a redshift of 7. So these are objects that are, of course, made out of stars, so we can't see individual stars with the Hubble Space Telescope. We can see the galaxies they reside in, and so maybe those 28 galaxies have enough energy, enough ultraviolet photons to reionize the universe. The idea is those galaxies form, they shoot photons out, and eventually, if there's enough around where each galaxy is, there will be a little bubble where hydrogen will be ionized. And when you have enough galaxies, those bubbles overlap, and the universe essentially goes from being neutral to being, once again, ionized.
So did we see enough of these galaxies to put out the ultraviolet we need?
Well, it turns out that it's unclear. And the reason is as powerful as the Hubble Space Telescope is, in this diagram, which is pretty complicated, we plot how faint we can see. So how faint in magnitudes we're looking back. So this is fainter and fainter and fainter, and this is the limit of how faint the Hubble Space Telescope can see. And this is very uncertain, the amount of ultraviolet photons that are produced from the galaxies that are seen.
And this is the amount you need to keep the universe reionized.
That's right. And you can see that right now, as faint as we can look, it doesn't appear that there's enough ultraviolet light to even have the universe stay reionized. Certainly not enough to make it reionized. So we seem to have a problem again. There's just simply not enough stuff in the universe that's glowing in the ultraviolet to reionize the universe.
And of course, we may well need it to be ionized before redshift 7, so we might even need to go further and find more distant objects, maybe at redshift 10 or 20, to get started. So one possibility is that the things we are seeing, even with the most sensitive observation ever made by the human race, are just too bright. For a galaxy to pick up, it must be a pretty bright galaxy at these enormous distances. It could be there are smaller galaxies out there. Each of them individually is not putting out much ultraviolet, but there could be large numbers of them, far more than the really mega galaxies, and between them they can put things together. That's what this up curve here is. If we could look much fainter than we can at the moment, maybe this curve will keep curving up, and eventually we might be able to see these fainter things.
And I should also say there's a little trick though as well, because the universe is full of dust, and it's hard for the ultraviolet light to even get out of its galaxy. So there could be lurking photons there that we simply don't see. So there's a calculation that needs to be made. And so some calculations say, well, maybe you don't need that many. You really need that many to ionize the universe. So there is a little bit of a question even still about how many galaxies we really need.
So right now the brute force approach, just trying to find these first lights, is kind of confused. We can see some galaxies at redshift 7. We can't yet see any at redshift 10 or 15. Those that are probably, but certainly not putting out enough ultraviolet, but we're only seeing the extremely bright galaxies. There could well be fainter ones that we're not seeing, and if we fudge all the different uncertainties together, maybe it can kind of work. What we'd really like to do is actually look fainter, see fainter things than we currently can do. And there are kind of two approaches. I suppose instead of spending merely a few months of time on the most expensive telescope on Earth staring at a blank bit of the sky, you could spend years staring at it. Hubble Space Telescope probably won't last that long. Another approach would be to build a bigger space telescope, and in fact the James Webb Space Telescope, which is scheduled for launch some point in the future if it doesn't get canned by Congress again, is designed to do exactly that, to look much fainter at more infrared wavelengths to try and spot these things. Or you can cheat. You can use what's called gravitational lensing. The idea is that clusters of galaxies in space actually act as natural lenses and focus the light, amplifying things behind them. We'll come back to that later in this course.